Welcome back. In this segment, we're going to discuss a fourth example of a proof by induction, a slightly different kind of theorem, and here it is. This theorem states that for all integers n, non-negative integers n, all possible sets with n elements have 2 to the power n subsets. So we're going to do a proof by induction on n again, and make sure we understand this theorem to be of the right form. This is saying for every element n in this set, we have P of n right here. So what is P of n? Well, P of n is saying all sets whose cardinality is n have a power set whose cardinality is 2 to the power n. That is a result that we've seen before, but finally we can prove it now by induction. So, let's start the basis step. The basis step is what? Is that the property P of n is true for n equals 0. Now remember, we're starting at 0 here again, so we can't start at 1. So what is P of 0? P of 0 says all sets with 0 elements have 2 to the power 0 subsets. So how many sets do we have with 0 elements? The answer is 1, that's the empty set. So what is the power set of the empty set? Well, the answer is the set containing the empty set. And what is the cardinality of that set? Well, the answer is 1. So now all we have to check is that 2 power 0 is also equal to 1, which of course it is. And therefore, we have proved that for all sets with 0 elements, then they each have 2 to the power 0 subsets. That's the conclusion of the basis step. Now let's turn our attention to the second subproof, the inductive step. This is where we assume that P of n holds for an arbitrary integer, and then we infer P of n plus 1. So let's assume P of n. In other words, assume that all sets with n elements have 2 to the power n subsets where n is an arbitrary non-negative integer. Again, you must make sure to include 0 here because 0 is included in the domain for n in the theorem. So now we have to prove P of n plus 1, that is, for all sets with n plus 1 elements, then they each have 2 to the n plus 1 subsets. So we have to prove a result for all sets of a given size. So we're going to pick an arbitrary set of that size, namely a set S whose cardinality is n plus 1. And don't forget, at the end we're going to have to do a universal generalization here. Since we took an arbitrary set of that size, whatever we're going to prove is going to be true of all sets of that size. But for now, we're going to work with a specific set S, an arbitrary set S. Now let's pick one element from that set and call it E. Now we're going to make sure for this step to be correct that E actually exists, and that is the case. Now why is that? Well, E must exist because n is at least 0, therefore the cardinality of S is at least 1, and since S contains at least one element, we are completely entitled to pick an arbitrary one of them, and let's call it E. So now we have a set with n plus 1 elements, one of which is E, and we're going to build a new set called S prime, which is simply what you get by removing E from S. Since S has cardinality n plus 1, S prime has cardinality n. It has one less element than than S, and that element is E. We just removed it from S. So, now what we're going to do is, well, we have a set of cardinality n plus 1. That set is S. Now we need to count the number of subsets of that set. How are we going to do that? Well, we can use the inductive or induction hypothesis and infer that S prime, whose cardinality is n, must have 2 to the power n subsets. And now we can use that fact to count the number of subsets of the set S, which is the one we're interested in. And the way we're going to do that is we're going to split all of the subsets of S into 2 groups defined as follows. Now remember that S is a set with n plus 1 elements, one of which is E. So if you look at all the subsets of S, some of them are going to contain E, and some of them are not going to contain E. And these are the 2 groups of subsets we're going to look at. So the first group are the subsets of S that do not contain E. How many of those are there? Well, we already have the answer to that question, because if you take S and you remove E, you get 2 to the power n subsets. Well, these subsets are exactly the subsets of S that do not contain E. So the number of subsets in the first group is 2 to the power n. Now, of course, there are the other group of subsets of S, those that actually contain E. And we also need to count those. Remember, a subset of S either contains E or does not. Now, it turns out the number of subsets of S that do contain E, there are also 2 to the power n of them. Now, why is that? Well, the intuitive answer is that for every subset that does not contain E, there corresponds a subset that does contain E, obtained by simply adding E to the subset in this group. So this is a little bit tricky to see. I encourage you to pause the video and work it out on a simple example. Let's say n is equal to 2. So S has size n plus 1 or 3. So let's take the set S equals A, B, C. And let's pick E to be, say, the element A. What I want you to do is find all the subsets of S. Split them into 2 groups, the one that don't contain A and the one that do contain A. And you should see that these 2 groups of subsets have the same number of sets in them, and that number is going to be 2 to the power n. Now, the total set of the subsets of S is obtained by unioning these subsets with these ones. Since a subset either contains E or it doesn't, and of course there's no common subsets in those 2 categories. So you take the union of them and you get the power set of S. Now the question is, how many elements are there in this power set of S? Well, the answer is this number plus this number. So in other words, the total number of subsets of S is 2 to the power n times 2, that's 2 to the power n plus 1. And that is exactly the statement of P of n plus 1. So in conclusion, this was true for the arbitrary set S. By universal generalization, it's true for every set of size n plus 1, and therefore P of n plus 1 holds. This concludes our proof of the inductive step, and together with our proof of the basis step, that concludes our proof by induction of Theorem 4.